You think you know terror? You don't. There are objects out there so dense, so gravitationally violent, that they rip space-time itself into pieces. They trap light, they bend reality, they eat stars whole. Black holes aren't just cosmic oddities for textbooks and documentaries. They're execution chambers where physics breaks, where time stops, where the universe forgets. And here's what nobody tells you. They come in different breeds. Each one more horrifying than the last. Some are born from dying stars. Others lurk at galaxy centers with masses billions of times our sun. A few hide in the gaps, missing links that shouldn't exist. And the most terrifying? The ones that might have spawned in the first second after the Big Bang, smaller than atoms but denser than anything you can imagine. Which ones are real? Which ones will kill you faster? What happens when you fall in? Let's find out. Before we go deeper, understand this. Black holes are execution machines with three simple specs. Mass, that's the fuel. More mass means more gravitational pull. A deeper gravity well that nothing escapes. Charge. Most black holes have basically zero charge because the universe balances itself out. Electrically charged objects attract opposite charges until they neutralize. But theoretically, a charged black hole can exist. It would have two event horizons instead of one, an inner and an outer boundary. The math works. Nature probably doesn't care. And spin. Black holes rotate. They drag space-time around them like a whirlpool, creating a region called the ergosphere where nothing can stay still. Stand there and you're forced to move with the black hole whether you like it or not. These three properties, mass, charge, and spin, define every black hole. The no-hair theorem says so. Everything else, the star that died, the matter that fell in, the information about what built it, gone, stripped away. The black hole remembers nothing except these three numbers. Stellar mass black holes, born from violence. When a star at least 20 to 25 times the mass of our sun exhausts its nuclear fuel, the core collapses, the outer layers rebound, supernova, the star explodes with the energy of 100 billion suns, visible across galaxies. What's left behind depends on mass. If the core remnant sits above 3 solar masses, neutron pressure fails, collapse continues, event horizon forms, you've got a stellar mass black hole. They range from about 3 solar masses up to 100 solar masses. Compact, deadly. Our Milky Way galaxy probably hosts around 100 million of them. Most are invisible, dark hunters drifting through interstellar space. We find them when they feed. Binary systems reveal them. A stellar mass black hole paired with a normal star pulls material off its companion. The stolen gas spirals inward, forming an accretion disk. Friction heats the disk to millions of degrees. X-rays scream out. We detect those X-rays, we measure the orbit of the companion star, we calculate the mass of the unseen object. If it's above 3 solar masses and compact, it's a black hole. No other explanation fits. Stellar black holes have been confirmed in systems throughout our galaxy. The closest one, Gaia BH1, sits about 1,500 light-years away. Another candidate, HR 6819, might be only 1,000 light-years out. These objects are our neighbors, cosmically speaking. June 2020 saw the smallest stellar mass black hole on record. The system, 2 mass J 05 2 15 6 58 plus 4 359 220 contains a black hole just 3.3 solar masses. Diameter, 19.5 kilometers. That's 12 miles across. A sphere small enough to fit inside a city, yet so dense that if you compressed Earth to the same density, it would shrink to less than an inch. The accretion disk around these objects glows in X-rays. Matter falling toward the event horizon accelerates to near light speed. Temperature climbs, 10 million degrees Kelvin, 20 million? Electrons stripped from atoms, plasma forms. The disk radiates across the electromagnetic spectrum but peaks in X-rays. Observatories like NASA's Chandra X-ray telescope hunt these signatures. Each detection confirms another stellar remnant crushed beyond neutron star limits into a black hole. But stellar mass black holes have a ceiling. Stars can't make black holes above about 65 solar masses. Stellar evolution theory predicts a mass gap. Between approximately 65 and 130 solar masses, stars undergo pair instability supernovae. At these masses, gamma rays in the core collide with atomic nuclei. Particle-antiparticle pairs form. Pressure drops. The core collapses partially. Runaway thermonuclear burning ignites. The star explodes completely. No remnant, no black hole, just expanding gas. This mass gap was theoretical until May 21st, 2019, 030229 UTC. Advanced LIGO and Advanced Virgo detected gravitational waves. Signal designation GW190521. The event was published September 2nd, 2020 in Physical Review Letters. The waveform matched two black holes spiraling together, masses 85 solar masses and 66 solar masses. The 85 solar mass object sits squarely in the pair instability gap. It shouldn't exist, not from a single star. The merger produced a black hole of 142 solar masses. 8 solar masses radiated away as gravitational wave energy. The first confirmed intermediate mass black hole, born from collision. Intermediate mass black holes, the missing link, between 100 and 100,000 solar masses, maybe as high as 1 million depending on definitions. For decades, these objects were hypothetical. Theory said they should form from mergers of smaller black holes in dense stellar environments like globular clusters. Or maybe from runaway collisions of massive stars and young galaxies, but detection proved difficult. They are too massive to form from single stars, too small to dominate galaxy centers like supermassive black holes. Observational evidence remained thin until recently. In November 2004, astronomers reported GCIRS-13E, a potential intermediate mass black hole orbiting 3 light-years from Sagittarius A star at the Milky Way's center. Mass, 1,300 solar masses. It sits within a cluster of 7 stars, possibly the remnant of a massive star cluster stripped down by the galactic core. However, a German research group in 2005 questioned whether this object truly qualifies as an intermediate mass black hole based on dynamical studies of the surrounding star cluster. Controversy remains. Another candidate, HLX-1 in galaxy ESO 243-49. This ultraluminous X-ray source likely harbors a black hole around 20,000 solar masses, possibly embedded in a stellar cluster with a total mass of 1 million solar masses. The system may be a remnant of a smaller galaxy, cannibalized by ESO 243-49. Observations suggest HLX-1 accretes matter periodically, flaring in X-rays when material falls onto the black hole. In 2020, astronomers announced 3XMM J21502 2.4-055108, a candidate intermediate mass black hole about 740 million light-years away in the direction of Aquarius constellation. In 2021, researchers posted a preprint to arXiv claiming discovery of a 100,000 solar mass black hole in globular cluster B023-G78 in the Andromeda Galaxy. In 2023, Einstein, analysis of proper motions in Messier 4, the closest globular cluster to Earth, revealed an excess mass of roughly 800 solar masses concentrated at the center. The mass concentration appears compact. Possible kinematic evidence for an intermediate mass black hole. The largest sample to date includes 305 candidates identified through sophisticated analysis of 1 million optical spectra from the Sloan Digital Sky Survey. X-ray emission confirmed 10 of these as likely intermediate mass black holes. Ultraluminous X-ray sources in star-forming galaxies, like those in starburst galaxy M82R, are suspected intermediate mass black holes with masses between 100 and 1,000 solar masses. They appear associated with young star clusters. But definitive confirmation requires dynamical mass measurements from analyzing optical spectra of companion stars orbiting the black holes. GW190521 changed the game. It proved intermediate mass black holes can form through hierarchical mergers. 2 stellar mass black holes, themselves possibly products of earlier mergers, collided. The resulting object crossed the threshold into intermediate mass. Gravitational wave detectors, LIGO and Virgo confirmed the event 17 billion light-years away. The black hole had a luminosity distance of 5.3 gigaparsecs, corresponding to a redshift of 0.82. The signal lasted 1/10 of a second, about 4 cycles in the 30 to 80 Hz frequency band, short, violent, definitive. The signal-to-noise ratio hit 14.7 across 3 detectors. False alarm rate? 1 in 4,900 years, using searches sensitive to generic transients. More detections followed. November 23, 2023. Gravitational wave signal GW231123 announced by the LIGO-Virgo-Kagura collaboration, another intermediate mass black hole merger. The rate of such mergers is estimated at 0.13 per gigaparsec cubed per year. Low. Rare, but real. Intermediate mass black holes populate the universe, hiding in globular clusters, dwarf galaxies, and dense stellar regions. They may be seeds for supermassive black holes, or they may be evolutionary dead ends. Objects too massive for stellar processes, but too light to anchor galaxies. Either way, they fill the mass gap. They exist, and they're terrifying in their implications. Black holes can cannibalize each other, growing larger with each meal. Supermassive black holes, galactic monsters, millions to billions of solar masses. They lurk at the centers of most large galaxies, including our own Milky Way. Sagittarius A star, pronounced Sag A star, abbreviated SGRAR A star. 4.297 million solar masses, with an uncertainty of plus or minus 0.012 million solar masses. That's the current best estimate based on observations of stars orbiting the black hole. Distance from Earth, 26,000 light years, give or take. The black hole sits near the border between constellations Sagittarius and Scorpius, about 5.6 degrees south of the ecliptic, close to the butterfly cluster. For decades, astronomers tracked stars circling apparently empty space at the galactic center. Star S2 completes an orbit every 16 years, reaching speeds up to 3% the speed of light. Its elliptical path focuses on a single invisible point. That point, Sagittarius A star, Reinhard Genzel and Andrea Ghez independently measured the orbits of giant blue stars around this unseen mass. Their work showed the central object had a mass exceeding 4 million suns, confined within a volume with radius no larger than 6.25 light hours, about 45 astronomical units. For comparison, the Schwarzschild radius of a 4 million solar mass black hole is 0.08 astronomical units, about 12 million kilometers. The object is compact, massive, dark. No known object except a black hole fits. Genzel and Ghez shared half the 2020 Nobel Prize in Physics for discovering that Sagittarius A star is a supermassive compact object, with a black hole as the only plausible explanation. May 12th, 2022. The Event Horizon Telescope collaboration released the first image of Sagittarius A star, 8 radio observatories across the planet, coordinated as a single Earth-sized virtual telescope, captured submillimeter radio waves from the black hole's vicinity. The image shows a dark central region, the black hole's shadow, surrounded by a bright ring of glowing gas. This is not the event horizon itself. That boundary emits no light. What we see is emission from superheated plasma orbiting just outside the event horizon, bent by intense gravity. The ring's diameter, about 14.6 million miles, 23.5 million kilometers. The Milky Way galaxy itself spans 100,000 light years. The black hole is a speck, but its gravity dominates the galactic core. Observations came from April 2017. Processing took years. Sagittarius A star's appearance changes rapidly. Matter orbits in minutes rather than hours or days, unlike the black hole in Messier 87, which stays relatively stable during observations. The team averaged thousands of images to produce the final result. It's the second black hole ever directly imaged, after M87 star in 2019. M87 star dwarfs Sagittarius A star. 6.5 billion solar masses versus 4 million, more than 1,000 times heavier. It sits 55 million light years away in the Virgo galaxy cluster, at the center of giant elliptical galaxy Messier 87. That black hole launches a relativistic jet, a stream of plasma and magnetic fields shooting out at near light speed for 5,000 light years. Sagittarius A star has no jet. It's starved, low matter supply, dim, relatively quiet. Yet both black holes look remarkably similar when imaged. Same ring structure, same shadow. This confirms general relativity predictions across vastly different scales. Gravity behaves the same whether the black hole weighs millions or billions of solar masses. How do supermassive black holes form? Nobody knows for certain. They can't grow from single stellar collapses. The mass is too large. One theory suggests hierarchical growth. Stellar mass black holes merge into intermediate mass black holes. Those merge into larger objects. Over billions of years, they accumulate mass until reaching supermassive scale. But observations of quasars, galaxies with intensely bright cores powered by supermassive black holes, show these objects existed when the universe was less than 1 billion years old. That's not enough time for slow hierarchical growth. Another hypothesis: direct collapse. In the early universe, massive gas clouds might have collapsed straight into black holes with masses around 10,000 to 100,000 solar masses, skipping the star formation stage entirely. These seed black holes then grew by accreting matter and merging with others. Primordial black holes, if they existed, might also serve as seeds. A third possibility involves dense stellar environments. In the cores of young galaxies, Runaway collisions of massive stars could build a single, very massive star that collapses into a seed black hole. Each theory has problems. None fully explains the observations. Supermassive black holes remain partially mysterious in origin. What we do know, almost every large galaxy has one. Observations with NASA's Hubble Space Telescope and other instruments confirm supermassive black holes at the centers of thousands of galaxies. Masses correlate with the galaxy's bulge mass. Bigger galaxy bulge, heavier black hole. The relationship suggests black holes and galaxies evolve together. The black hole influences star formation and gas dynamics in the surrounding region. Active galactic nuclei. Extremely bright cores powered by supermassive black holes gorging on matter A can outshine entire galaxies. The energy released as matter accelerates toward the event horizon drives galactic winds that blow gas out of the galaxy. Regulating star formation, black holes don't just sit passively, they shape their host galaxies. The largest known supermassive black hole sits in galaxy Holmberg 15A, mass, at least 40 billion solar masses. That's 10,000 times heavier than Sagittarius A star. Astronomers estimate some supermassive black holes could reach 100 trillion solar masses during the collapse of superclusters of galaxies. Though these are theoretical upper limits, even at 40 billion solar masses, Holmberg 15A's black hole is incomprehensibly massive. Its event horizon would have a diameter large enough to engulf our entire solar system out past Neptune's orbit. If you fell toward it, tidal forces would remain relatively weak until you approached the singularity deep inside. You'd cross the event horizon almost comfortably. Then the crushing would begin. Supermassive black holes spin, most rotate at significant fractions of the maximum possible rate. When black holes merge, they conserve angular momentum. Spin rates can change. The Kerr metric describes rotating black holes mathematically. It predicts an ergosphere, a region outside the event horizon where space-time itself rotates. Inside the ergosphere, you can't stand still. You must orbit with the black hole. Frame dragging, relativity in action. The rotating black hole drags space-time along. Escape is possible from the ergosphere, unlike from inside the event horizon, but you'll work hard to get out. The Penrose process theoretically allows energy extraction from a rotating black hole by dropping matter into the ergosphere and having part of it escape with more energy than it entered. Theoretically, nobody's tested it. Primordial black holes, hypothetical, born in the first second after the Big Bang. When the universe was dense and hot, quantum fluctuations in energy density might have created regions compressed enough to collapse directly into black holes. No stars needed. These objects could have masses ranging from 100,000 times less than a paperclip, about 10 to the negative fifth grams, up to 100,000 solar masses. Formation window? Approximately 1 second after the Big Bang. After that, the universe expanded and cooled too much for primordial black holes to form. Stephen Hawking explored their quantum mechanical properties in the 1970s. He realized small black holes could evaporate through what's now called Hawking radiation. Quantum effects near the event horizon cause particle-antiparticle pairs to separate. One particle escapes. The other falls in with negative energy. The black hole loses mass. Over time, it shrinks. Temperature increases inversely with mass. Small black holes are hotter, radiating more intensely. A primordial black hole with the mass of a mountain would have evaporated by now. Larger ones might still exist. A primordial black hole of about 100 billion kilograms would evaporate in roughly 2.6 billion years. Hawking radiation has never been directly observed from any black hole. The temperature for stellar mass and supermassive black holes is absurdly low, around 10 to the negative 14th Kelvin for a solar mass black hole, far below the cosmic microwave background temperature of 2.7 Kelvin. They absorb more energy from the universe than they radiate. They grow, not shrink. Only primordial black holes small enough to be evaporating now would emit detectable radiation. NASA launched the Fermi Space Telescope in June 2008 to search for terminal gamma-ray flashes from evaporating primordial black holes. None detected. Either primordial black holes don't exist, or they're too rare. Or they're too massive to evaporate in the current age of the universe. Some physicists propose primordial black holes as dark matter candidates. Dark matter makes up about 85% of the universe's matter, but doesn't interact with light. We detect it only through gravitational effects. If primordial black holes with specific mass ranges exist in large numbers, they could account for dark matter. But constraints from various observations, including gravitational lensing and cosmic microwave background measurements, limit the allowed mass ranges. Most parameter space is ruled out. Primordial black holes likely aren't the dominant component of dark matter. Another possibility, primordial black holes as seeds for supermassive black holes. If primordial black holes formed with masses around 10,000 to 100,000 solar masses, they could serve as starting points for growth into galactic center monsters, but the formation time constraint creates problems. Primordial black holes had to form within the first second. Physics suggests they'd max out around 100,000 solar masses. To reach billions of solar masses, observed in early quasars, they'd need to accrete matter very rapidly. Possible, but difficult. The question remains open. Researchers continue hunting for primordial black holes. One method, searching for gravitational lensing effects. When a compact massive object passes between us and a distant star, it bends light, temporarily brightening the star. Primordial black holes would create specific lensing signatures. Surveys monitor millions of stars looking for these events. Another approach, analyzing gravitational wave data for mergers. Involving objects in the primordial black hole mass range. If detected, these would provide direct evidence. So far, nothing conclusive. Primordial black holes remain theoretical, tantalizing, but unconfirmed. If you value documented astrophysics and observational cosmology like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from physical review letters. The peer-reviewed journal that published the GW190521 discovery on September 2nd, 2020 in volume 125C, page 101102. Authored by the LIGO Scientific Collaboration and Virgo Collaboration. We also rely on data from the Event Horizon Telescope Collaboration's May 12, 2022 release of the Sagittarius A-star image, published simultaneously across multiple journals and announced at simultaneous press conferences worldwide. NASA's October 22, 2024 update on black hole types from their official science website provides mass ranges and formation mechanisms. And we draw from Nature Communications' December 18, 2012 article by Jenny Green on low-mass black holes as remnants of primordial black hole formation, examining intermediate mass black hole candidates in galaxy centers. These aren't blog posts or science journalism. These are the original research papers and institutional sources. Now back to the information. Charged black holes, Reissner-Nordström geometry. Theoretical. Discovered independently by Hans Reissner in 1916 and Gunnar Nordström in 1918, these are black holes with mass and electric charge but no spin. Real black holes probably don't carry significant charge. The universe appears electrically neutral. A charged black hole would quickly attract opposite charges from surrounding matter, neutralizing itself. But mathematically, charged black holes are fascinating. They have two event horizons, an outer and an inner. Unlike the single horizon of an uncharged Schwarzschild black hole, the inner horizon is sometimes called the Cauchy horizon. Between the horizons, space-time behaves strangely. Across both horizons inward, and space and time swap roles twice. Inside the inner horizon, you might avoid the singularity. Theoretically, the singularity in a charged black hole is different from a Schwarzschild black hole. It's time-like rather than space-like. You could, in principle, steer around it, but the Cauchy horizon is unstable. Perturbations from outside get infinitely blue-shifted as they approach the inner horizon. An observer crossing it experiences an eternity of external events compressed into finite time. You'd be bombarded with infinitely energetic radiation. Survival? Unlikely. Charged black holes come in subextremal, extremal, and superextremal varieties. Subextremal. Charge less than mass in appropriate units. Two distinct horizons. Extremal. Charge equals mass. The two horizons merge into one. The temperature drops to 0. Hawking radiation stops. The black hole becomes stable thermodynamically. Superextremal. Charge exceeds mass. No horizons form. The singularity is naked, exposed to the outside universe. Most physicists believe naked singularities can't exist. Cosmic censorship conjecture states that singularities must be hidden behind event horizons. Superextremal charged objects might exist in nature, objects with charge exceeding mass, but they wouldn't collapse into black holes. Theories with supersymmetry generally prohibit superextremal black holes. Observations support this. No confirmed charged black holes exist. We see only uncharged or nearly uncharged black holes in nature. Charge is theoretically possible. Nature doesn't seem interested. Rotating black holes, Kerr-metric. Discovered by Roy Kerr in 1963. This describes a black hole with mass and spin, but no charge. Most real black holes likely fit this description. Stars rotate. When they collapse, angular momentum is conserved. The resulting black hole spins. The Kerr solution is more complex mathematically than the Schwarzschild or Reissner-Nordström solutions. It took decades after Einstein published general relativity in 1915 before Kerr found the rotating solution. The geometry is significantly different. The singularity is a ring, not a point. The event horizon is oblate, flattened by rotation. Outside the event horizon lies the ergosphere, where frame dragging occurs. Space-time rotates with the black hole. You cannot remain stationary. Inside the ergosphere, but outside the event horizon, escape is possible if you move in the right direction. Cross the event horizon and you're done. No escape. The inner structure of a Kerr black hole includes an inner horizon similar to charged black holes. The inner horizon suffers the same instability problems. In practice, astrophysical black holes likely don't have stable inner horizons. Perturbations destroy them. The actual internal structure remains unknown. We can't see inside, and we'll never escape to report what we find. Kerr-Newman metric. Most general black hole solution, mass, charge, and spin. Discovered by Ted Newman and collaborators in 1965. This combines the Reissner, Nordström, and Kerr geometries. 2 horizons. Rotating singularity, ergosphere, charge, mathematically complete, physically unlikely. Real black holes probably spin, but don't hold significant charge. Kerr-Newman remains a mathematical curiosity, a complete solution to Einstein-Maxwell equations describing gravity and electromagnetism together. It's beautiful, probably irrelevant to nature. The no-hair theorem, John Wheeler proposed it. Black holes have no hair, meaning, outside the event horizon, a black hole is characterized entirely by 3 properties: mass, charge, spin. Nothing else matters. Doesn't matter if the black hole formed from a hydrogen cloud, a textbook, a planet, or a supernova remnant. All information about the progenitor is lost. Only mass, charge, and spin remain. The theorem applies to isolated, stationary black holes. It's been proven mathematically for various cases, though some exotic scenarios with specific matter fields might evade it. For realistic astrophysical black holes, the no-hair theorem holds. This connects to the black hole information paradox. If black holes erase all information except 3 numbers, and then evaporate through Hawking radiation, which appears thermal and random, where does the information go? Quantum mechanics says information can't be destroyed. General relativity says it falls into the black hole and disappears when the black hole evaporates. Paradox. Stephen Hawking initially argued information is lost. Later, he changed his mind, proposing information might be encoded in subtle correlations in Hawking radiation. The debate continues. No consensus. The information paradox remains unsolved, one of the deepest problems in theoretical physics. Hawking radiation itself deserves attention. In 1974, Stephen Hawking calculated that black holes aren't entirely black. Quantum field theory in curved spacetime predicts particle creation near the event horizon. Virtual particle-antiparticle pairs fluctuate into existence throughout space. Near a black hole's horizon, the extreme spacetime curvature can separate the pair before they annihilate. One particle escapes. The other falls in with negative energy relative to an external observer. The black hole loses mass. The escaping particles constitute Hawking radiation. The radiation has a thermal spectrum characterized by temperature inversely proportional to mass. Lower mass means higher temperature. A solar mass black hole has a temperature around 10 to the negative 7th Kelvin. A supermassive black hole of 1 billion solar masses, 10 to the negative 14th Kelvin. Absurdly cold, far below the cosmic microwave background. These black holes grow, not shrink. Only tiny primordial black holes would be hot enough to evaporate noticeably. A mountain mass black hole, about 10 to the 11th kilograms, has a temperature around 10 to the 11th Kelvin. It radiates intensely. Lifetime? A few seconds. These would explode in gamma rays. Fermi telescope looks for such events. None found. A solar mass black hole, if isolated in empty space far from the cosmic microwave background, would take 10 to the 67th years to evaporate. That's 10 trillion years. The current age of the universe is about 14 billion years. The black hole outlasts the universe by an incomprehensible margin. A supermassive black hole of 100 billion solar masses, 2 times 10 to the 100th years. Evaporation timescales are absurd. Black holes will outlive stars. Galaxies, as and everything else. Eventually, in the far future, black holes will be the last significant structures in the universe. Then they too will evaporate. The universe ends in a thin gas of photons and elementary particles. Heat death. But not for eons beyond comprehension. Recent research by Michael Wondrak, Walter van Zwijlekam, and Heino Falke at Radboud University published in Physical Review Letters on June 2, 2023, showed Hawking was partially correct. Black holes do evaporate, but the event horizon isn't as crucial as believed. Space-time curvature itself, even far from the horizon, can create particle pairs through gravitational effects. This means not only black holes, but any massive object will eventually radiate and evaporate. Stars, planets, everything. The timescales are even longer than black hole evaporation, but the principle holds: given infinite time, everything decays. The universe trends toward maximum entropy. The second law of thermodynamics plays out on cosmic scales. All structure dissolves. Only formless energy remains. Observations continue. Gravitational wave detectors, LIGO. Virgo and Cagra now regularly detect black hole mergers. Each event provides data on black hole masses, spins, and merger dynamics. The population of black holes is more diverse than expected. Some black holes spin rapidly, near the maximum allowed by physics. Others spin slowly or not at all. Some mergers involve nearly equal mass partners. Others are asymmetric. The distribution of masses shows peaks and gaps. The mass gap around 65 to 130 solar masses, predicted by pair instability supernovae theory, is real but not absolute. GW 190521 proved black holes can populate the gap through mergers. The rate of mergers increases as we look back in time, toward the early universe when galaxies were smaller and denser. Black holes merged more frequently then. The merger rate depends on the initial mass function of stars, the fraction of stars massive enough to form black holes, and the dynamics of dense stellar environments. Radio astronomy reveals supermassive black holes across the universe, quasars. Intensely bright galactic cores powered by accreting supermassive black holes were more common in the early universe. Billions of years ago, galaxies fed their central black holes more readily. Gas was abundant. Star formation rates were higher. Black holes grew rapidly. Today, many supermassive black holes are quiescent, starved of matter. Sagittarius, A star accretes materials slowly, generating relatively little radiation. M87 star actively feeds, powering its jet. The jets themselves are mysteries. How do black holes launch collimated streams of plasma at relativistic speeds? Magnetic fields play a role, twisted and amplified by the rotating accretion disk and the black hole's spin. The Blandford-Zanajek process extracts rotational energy from the black hole, converting it into electromagnetic energy that powers the jet. Simulations match observations reasonably well. Details remain uncertain. The Event Horizon telescope expands. More telescopes join the array. Observing frequencies diversify. Resolution improves. Future images will capture black holes in motion. Movies, not still frames, we'll watch matter orbit and plunge across the event horizon. We'll see jets launch. We'll measure spin more precisely. Polarization data. Released for Sagittarius A star in 2024, reveals magnetic field structure around the black hole. The fields are tangled near the event horizon, likely chaotic. Farther out, they align with the accretion disk. Understanding these fields helps explain how energy is transported and radiated. Polarized light traces magnetic field orientation. Observing it provides a diagnostic tool for conditions near the event horizon. Black hole physics pushes the boundaries of known science. General relativity describes space-time curvature. Quantum mechanics describes matter and energy at small scales. Black holes force these theories together. Near the singularity, both matter density and space-time curvature become infinite. General relativity breaks down. Quantum effects dominate. We need a theory of quantum gravity. String theory proposes one possibility. Loop quantum gravity offers another. Both remain speculative. No experimental tests yet. Predictions differ in details. Neither is proven. Black holes might provide a testing ground. Hawking radiation, if detected, would confirm quantum effects in curved spacetime. Deviations from general relativity predictions near black holes could signal new physics. So far, general relativity passes every test. The Event Horizon Telescope images match predictions. Gravitational wave signals follow the waveforms calculated from general relativity. If quantum gravity effects exist, they're subtle. We need better instruments, more data, patience, black hole shadows. The dark region in the center of Event Horizon Telescope images, it's not the event horizon itself, it's the photon sphere, light orbiting the black hole at a critical radius. Inside that radius, photons spiral inward and get captured. Outside, photons can escape to distant observers if aimed correctly. The photon sphere radius depends on black hole mass and spin. For a non-rotating Schwarzschild black hole the photon sphere sits at 1.5 times the Schwarzschild radius. For a rotating Kerr black hole, the radius depends on the viewing angle and spin rate. Photons can orbit closer to the horizon on the equator if moving with the black hole's rotation. Against the rotation, they must stay farther out. The shadow is larger if we view the black hole face on, looking down the spin axis. Smaller if edge on. Measurements of shadow size and shape constrain mass and spin. Sagittarius. A star's shadow appears circular, suggesting we're viewing it at an intermediate angle. M87 star's shadow is also roughly circular, but slightly asymmetric. These observations confirm black hole properties derived from other methods. Consistency builds confidence. Tidal forces, spaghettification. Falling toward a black hole, you experience differential gravity. Your feet, closer to the singularity, feel stronger pull than your head. The difference stretches you. For a stellar mass black hole, tidal forces become lethal far outside the event horizon. You're ripped apart before reaching the point of no return. For a supermassive black hole, tidal forces at the event horizon are weak. You cross safely. The gradual stretching begins deeper inside, approaching the singularity. A 1 solar mass black hole has a Schwarzschild radius of about 3 kilometers. Tidal forces near the horizon are intense. A 4 million solar mass black hole like Sagittarius A star has a Schwarzschild radius of 12 million kilometers. Much gentler gradients. You'd survive to the horizon. Past it, though, you accelerate inward. Space-time curvature increases. Tidal forces grow. Eventually, they tear you apart, atom by atom. The singularity approaches. Density diverges. Your remnants compress to infinite density. Or, if quantum gravity intervenes, something else happens. We don't know. Nobody's tested it. Time dilation, gravitational redshift, clocks run slower in strong gravitational fields. Near a black hole, time slows dramatically relative to distant observers. If you hover just outside the event horizon of a stellar mass black hole, your clock ticks far slower than one in interstellar space. Watch a distant star, it ages rapidly from your perspective. Billions of years pass out there while you experience minutes. Fall toward the horizon and the effect intensifies. At the event horizon itself, time stops from the external viewpoint. Light emitted by you redshifts infinitely. External observers never see you cross the horizon. You appear frozen, dimming exponentially, fading from view. From your perspective, you cross the horizon in finite proper time. No barrier, no special moment. The universe outside blue shifts. Light from the universe's future floods in. You glimpse the end of time as you fall past the point of no return. Then darkness. The singularity awaits. Your timeline ends. The universe continues without you. Ergosphere energy extraction. Penrose process. Hypothetical but theoretically sound. A particle entering the ergosphere of a rotating black hole can split into two. One fragment falls into the black hole with negative energy relative to a distant observer. The other escapes with more energy than the original particle carried. Net result, energy extracted from the black hole's rotation. Do this enough, and you slow the black hole down, extracting rotational energy. Advanced civilizations might harvest energy this way. No violations of thermodynamics. The black hole's rotational energy decreases. Its event horizon area increases slightly, keeping the second law of black hole thermodynamics satisfied. Another method, superradiance. Waves entering the ergosphere with specific frequencies can be amplified and escape, carrying away more energy than they brought in. Rotational energy fuels the amplification. Again, the black hole spins down, theoretically elegant, practically irrelevant unless we build megastructures around black holes. Nobody has yet. Binary black holes. Two black holes orbiting each other. When close enough, they emit gravitational waves. The orbit decays, separation shrinks. Orbital period decreases, gravitational wave frequency increases, amplitude grows. In the final moments before merger, the black holes spiral together rapidly. They collide, horizons merge, a single, larger black hole forms, ringing like a struck bell. The ring-down phase emits gravitational waves at characteristic frequencies determined by the final black hole's mass and spin. The entire process from inspiral through merger to ring-down is encoded in the gravitational wave signal. LIGO, Virgo, and Cagra detect these signals. Parameter estimation algorithms extract masses, spins, distance, and sky location. Each detection adds to our catalog of black hole properties. The population synthesis improves. We learn how black holes form, how they pair up, how they merge. Astrophysics and cosmology advance with each event. Accretion disks, matter falling toward a black hole doesn't plunge straight in. Angular momentum forces it into orbit. The gas forms a disk, spiraling inward over time. Viscosity. likely driven by magnetic turbulence, transports angular momentum outward. Material moves inward. Friction heats the disk. Temperature depends on radius and black hole mass. For stellar mass black holes, inner disk temperatures reach millions of Kelvin. X-rays dominate emission. For supermassive black holes, temperatures are lower, peaking in ultraviolet or optical wavelengths. Accretion disks power quasars, active galactic nuclei, and X-ray binaries. Efficiency is impressive. About 10% of infalling matter's rest mass energy converts to radiation. Compare that to nuclear fusion, which converts less than 1%. Black holes are the most efficient power sources in the universe. Observing accretion disks tells us about matter under extreme conditions. Density, temperature, magnetic field strength, all pushed to limits. Plasma physics in a regime we can't replicate in labs. Corona, hot, tenuous gas surrounding the accretion disk. Electrons in the corona are heated to hundreds of millions of Kelvin. They scatter disk photons, upscattering them to X-ray energies. The resulting X-ray spectrum shows a power law continuum and often an iron emission line at 6.4 kilo-electron-volts. The iron line is broadened and skewed by Doppler shifts and gravitational redshift. Its shape encodes information about the black hole's spin and the disk's inner radius. Fitting models to observed spectra constrains black hole properties. This technique complements gravitational wave and imaging observations. Multiple independent methods agree. Consistency across techniques builds confidence. Quasi-periodic oscillations. X-ray emission from accreting black holes sometimes shows periodic or quasi-periodic brightness variations. Frequencies range from millihertz to kilohertz, depending on black hole mass and accretion state. The oscillations reflect dynamics in the inner accretion flow. Orbital motion, precession, and magnetic instabilities all contribute. High-frequency quasi-periodic oscillations near the innermost stable circular orbit are particularly interesting. That orbit marks the boundary inside which matter cannot stably circle the black hole. It must plunge inward. The radius depends on black hole spin. Measuring oscillations constrains spin. Data from X-ray telescopes like RXTE, XMM Newton, and NuSTAR provide these measurements. Thousands of black holes observed, spins estimated. Most stellar mass black holes and X-ray binaries spin moderately to rapidly. Distribution suggests formation channels favor spinning black holes. Supermassive black holes show diverse spins. Some spin rapidly, others slowly. Growth history matters. Mergers tend to produce high spin if aligned. Chaotic accretion reduces spin. Soft X-ray transients. Low-mass X-ray binaries where the black hole alternates between quiescent and outburst states. Most of the time, accretion is slow. The black hole is dim. Periodically, the disk becomes unstable. Matter floods inward. X-ray brightness spikes by factors of thousands or millions. Outburst lasts months, then the disk depletes. Accretion drops. The system returns to quiescence. The cycle repeats irregularly. Observers monitor dozens of these systems. Each outburst provides data on accretion physics, disk structure, and black hole properties. Some systems have been observed for decades. Long-term trends emerge. Variations in outburst behavior reveal changes in the disk or companion star. Companion stars and black hole binaries evolve. Roche lobe overflow drives accretion. The companion expands as it ages. Eventually, it overfills its Roche lobe. Matter spills onto the black hole. If the companion is massive, it may explode as a supernova, potentially disrupting the binary or creating a second black hole. If the companion survives, the system becomes a double black hole binary. These eventually merge, detectable by gravitational wave observatories. Formation channels for merging black holes are complex, primordial binaries. Dynamical captures in dense clusters, hierarchical triples. Each channel predicts different mass ratios, spin alignments, and merger rates. Observations constrain the contributions. Population synthesis models evolve. Matching theory to data is an ongoing process. Black hole kicks. Supernova explosions that create stellar mass black holes can be asymmetric. More matter ejected in one direction than others. The black hole recoils. Kick velocities can reach hundreds of kilometers per second. Some black holes are ejected from their birth clusters or even their host galaxies. Orphan black holes drift through intergalactic space. Others remain bound but move to high galactic latitudes. Observations of black hole binaries at large distances from the galactic plane suggest natal kicks. Gravitational wave observations also hint at kicks. Merging black holes with unequal masses or misaligned spins produce asymmetric gravitational wave emission. The final black hole recoils. Kick velocities up to 5,000 kilometers per second are possible for extreme configurations. These black holes might escape their host galaxies, becoming wanderers. Rogue black holes wandering through the galaxy, stellar mass black holes ejected from clusters or given large natal kicks. Intermediate mass black holes from disrupted globular clusters or dwarf galaxies. These objects are hard to detect unless they accrete matter. Most drift invisibly. Occasionally, one passes through a molecular cloud or encounters a star. Accretion flares. We see a transient X-ray source or gravitational lensing. A foreground black hole passes between us and a background star. The star brightens temporarily. Microlensing surveys watch for these events, rare but detectable. Each event constrains the population of rogue black holes. Current estimates suggest millions of stellar mass black holes in the Milky Way, most invisible. A few thousand are in binaries where we can detect them, the rest hide in darkness. Primordial black holes, if they exist, would also be wanderers. Formed in the early universe, they'd be scattered throughout the cosmos by cosmic expansion and gravitational interactions. Detection would require careful observation. Gravitational lensing, accretion signatures, dynamical effects in star clusters, decay radiation if small enough. So far, no definitive detection. But absence of evidence isn't evidence of absence. Primordial black holes might lurk in parameter spaces we haven't thoroughly searched. Future surveys with improved sensitivity might find them, or rule them out conclusively. Black hole shadows and photon rings. Beyond the bright ring in the event horizon. Telescope images, theoretical calculations predict a series of fainter photon rings. Light that orbits the black hole multiple times before escaping. Each ring is thinner and dimmer than the last. The ring spacing encodes black hole properties independent of the surrounding matter. Detecting these rings would test general relativity in a new regime. Current imaging resolution isn't sufficient. Future upgrades to the Event Horizon Telescope or next-generation instruments might resolve photon rings. The payoff, a pure gravitational signature, uncontaminated by astrophysical uncertainties. A direct probe of space-time geometry near the event horizon. Gravitational wave echoes, hypothetical. If the event horizon has structure at small scales, maybe from quantum gravity effects, gravitational waves produced near the horizon might partially reflect, creating echoes. These would arrive delayed relative to the primary signal. Searches in LIGO-Virgo data for echoes have been performed. No convincing detections. The idea remains speculative. Most physicists doubt echoes exist, but the search continues because the payoff would be enormous. Evidence for quantum structure of space-time, a glimpse beyond classical general relativity, wormholes. Hypothetical tunnels through space-time connecting distant regions. The interior of charged or rotating black holes, according to the Reissner-Nordstrom or Kerr solutions, contains mathematical wormhole structures, but these are unstable. The inner horizon is unstable to perturbations. Realistic black holes formed from stellar collapse likely don't have traversable wormholes. Even if they did, crossing would be fatal. Tidal forces destroy you. And the wormhole likely pinches off before you can pass through. Exotic matter with negative energy density might hold a wormhole open, but no known matter has that property. Wormholes remain science fiction, mathematically interesting but physically implausible. Black holes are not shortcuts, they're dead ends. Now the reveal. In April 2024, researchers using the Atacama Large Millimeter Array detected a gas cloud orbiting an invisible object near Sagittarius A star, with orbital characteristics matching a black hole of intermediate mass. 23 light-years from the galactic center, this potential intermediate mass black hole of several thousand solar masses could eventually merge with Sagittarius A star. If confirmed, it demonstrates that intermediate mass black holes do wander through our galaxy's core, exactly where hierarchical merger theories predict they should accumulate. The black hole isn't visible, the gas stream reveals it. Velocity measurements constrain mass. Follow-up observations will refine the estimate and determine if this object is truly an intermediate mass black hole or something else. Either way, the galactic center is more crowded than expected. Black holes populate it. They orbit. They merge. Sagittarius A star grows. In tens of millions of years, if this intermediate mass black hole falls in, gravitational waves will ripple across the galaxy. We won't be here to measure them. But the black hole won't care. It never does.